Okay, let's start. The second speaker of this morning session is Professor Shuangqian Liu, and the title is the 3D kinetic Couette flow via the Boltzmann equation in the diffusive limit.
Thanks for the introduction and thanks for the invitation. I'm very pleased to join this nice conference. And I also apologize, I'm not good at speaking English. I try to speak it, okay? Today I'm going to talk about the hydrodynamic limits of the Boltzmann equation in a finite channel, okay? The hydrodynamic limit of Boltzmann equation is a class problem that can date back to 1900. Here proposed is 23 famous problems. This problem is related to the sixth problem, and we start with this model. This is a scale Boltzmann equation. And the left-hand side, the transport operator, and the right-hand side, the Collision-Boltzmann operator. Here we consider the diffusive reflection boundary condition. And F super epsilon is the density distribution function of dilute gas. Okay, it is the function of the time variable t, spatial variable x, and the velocity variable v. So basically, it is non-negative because it's the density distribution function. The second term, we call it the convection term. However, it is different from the usual convection term, such as the convection term in Euler equations or Navier-Stokes equations. Here V is here V is the argument of F. X is also an argument of F. So this V can be this V is in R3. Okay, it can cross. Okay, and this guy is the V is the artificial external force. We put this term here just to make our solution non-trivial. Okay, and this small parameter that epsilon is called the Lewis number. It represents the ratio of the mean free path and the characteristic length. When this epsilon becomes small, that means the dilute gas becomes denser. So in this situation, we cannot describe the dynamic of gas by this Boltzmann equation. It will be described by the classical fluid equation, such as the Navier-Stokes equation or Euler's equations. So when epsilon goes to 0, we want to know if this solution can be go to the solution determined by the Navier-Stokes equation or the Euler's equations. That's our aim for this talk. Okay, and here this is the classical reflection diffuse reflection boundary condition, and the domain is the finite channel. That means the x direction and y direction are periodic. Okay, and the z direction is a straight. Is an interval, okay? It's confined in -1 to 1, okay? And it's also different from the classical PDE boundary conditions. Here, the boundary is described by the free space. It means it's related to the z variable. It not only relates to z variable, but also relates to the v variable, okay? And also, this is a map. Okay, it's also a distribution. Okay, this guy is the Gaussian. Okay, and has for this variable, it has a shift, okay? Here, u1 does not equal to u minus 1. It means there is a relative motion at the boundary. I can write here. There is a u up epsilon velocity, and on the up, the down, there is on the bottom there is a minus up epsilon velocity. So this, due to this relative motion at the boundary, it can reduce a long travel solution. Okay. Here we put the external force here. Just want to make our solution come from the solution determined by the classical fluid equation can be non-trivial. I will explain this external force later. Okay. For this Boltzmann collision operator, we can give its expression in this form. Generally speaking, it includes two parts. One is the collision color. This is called collision color. It is a function of the relative velocity and also the deflection angle. Okay, this is the deflection angle, and we consider this form, and this parameter gamma is between 0 and 1. It means we consider the hard potential case, and there is also another physical case. It's called the soft potential. It means gamma takes the value between -3 to 0. Okay. Here we just consider this case for the mathematical techniques. Okay. And the other part is the probability distribution of the collision. It means two independent events occur at the same time, so there is a product. Okay. This is the incoming part. This is the outgoing part. Okay. So we look for solutions in this form. Okay. It means there is a shift along the Vx direction, and in this form, by plugging this form into the original equation, we can got this equation for this epsilon, f super epsilon, and naturally there are two new terms. Okay, this term and this term just come from this shear force. Okay, this shear force. Okay, and for this guy, as I have talked in the first page, where when us grows, because V is in R3. So this is different from the original equation, and it does create difficulties with this because of these two new terms. Okay, but the advantage of this transformation is that now boundary is standard. Okay, I have right here because of the relative boundary, the relative motion at the boundary is very difficult. But now, due to this transformation, the boundary now is normalized. This is the classical Gaussian. Okay, it's normalized Gaussian. Okay, this Gaussian, in fact, from the famous H theorem of the kinetic theory, this Gaussian is equilibrate. It means nu satisfies the right hand side this color. Okay, this operator. Okay, we let f epsilon, f super epsilon to this guy, then this values. Okay, and since this is dynamic problem, we have to impose this initial data. Then how to consider this problem, this dynamic problem? We start from this non-dynamic, okay, this unsteady problem. So we consider the steady problem, and we expect the long time behavior of the in static program can be governed by this static program. That means we ask this solution does not depend on the time variable. Okay. And also there's a physical condition, the mass is conserved due to the boundary domain, and there is no particles going out and no particles going in the interior. So just reflection, just the reflection. Okay. And then we start from the stem problem. We further look for solutions in this expansion. It is also called the diffuse expansion. That's why we call the title called the diffusion limit. Okay, this is the diffusive expansion. It is slightly different from the famous Hilbert expansion. This global Maxwell is the equivalent of the Boltzmann equation, and I also put a weight here, nu 1/2. It's standard, because if we have this nu 1/2, then the linearized operator L is self-adjoint. Okay, that means we can also obtain the causality estimate of this operator. Okay, and F1 is the first corrector, F2 is the second corrector, and the FR is the remainder. And we can say that this guy is not later, because if this one is the power is epsilon 1, then this should be epsilon square. Okay, but we cannot do this because due to the mathematical techniques. Okay, I will explain this later. Okay, why we just put epsilon 1/2 here, not epsilon square. Even more, we cannot put epsilon the power bigger than the 1. Okay. Then we plug this expansion into the static program, and we got the equations for the first coefficients F1. Okay, governed by these two equations, and F2. Okay, this guy, also this guy, and also this guy determine the F2. Okay, F1 is determined by this one. Okay, also this one. And the remainder equation now becomes complicated. Okay, because we do the expansion, and just as I have talked, there are two troubles. Okay, this guy stems from the shear force. Okay, when this derivative acts to the mu 1/2, then there is another Vx. There is another Vx, and there is a Vz. So the growth becomes square. There is a square growth. Okay, in V. And this also another growth caused by the external force. But this growth is, the power of the growth is square, but this is just 1. So if we can control this guy, then this guy can be also controlled. Okay. And just plug the expansion into the boundary, we can got the this standard diffusive boundary projection. It's a projection. It means that we can use this transport term and to handle this projection. Okay, and there's error term just from the second correction, and here we must have this factor 1/2, because if it's not 1/2, then we cannot control this guy. Okay, that's why we just have factor in front of the remainder epsilon 1/2, because if this guy, sorry, if this guy is high, just because just for example, it takes 1, then this will be minus. Okay, then we cannot control this guy. If we want to lift the power of the remainder, I think we should consider the loose layer. So this guy will vanish if we introduce the loose layer. Now we go back to the first coefficient F1 by this equation below. F1 is just purely macroscopic. Macroscopic also called the fluid component. Fluid. Okay. There are 5 quantities: the density rho s, the velocity us, and the temperature θs. And by the momentum integration, we can obtain the classical Navier-Stokes Fourier system around the Couette flow after t 0, 0. Okay, the blue words just the term caused by the Couette flow. Okay, and this is the standard problem, also elliptic problem. Okay, and we can solve these equations to get the estimate for rho, u, and theta. Once F1 is determined by this equation, we can move to the second coefficient F2. It is Couette formula. That means if F1 is determined, F2 can also be determined by this formula. This is totally related to the F1, and this is the macroscopic part of F2. This is the microscopic part of F2, US2 and θS2. US2 is determined by this formula, and the θS2 is determined by pressure. Okay, so it is also a traditional problem. Okay, to solve this Navier-Stokes equation, you should solve the pressure first. Okay, and once the pressure is solved, then we can obtain the estimate for SZ2. Okay. Now we move to the remainder. How to deal with the growth caused by shear force? We introduce the capture decomposition. The treatment of this decomposition is that we split the solution into two components. Okay, one component there does not include one half. Okay, this weight, there's no weight, but the other does have the weight. Due to this decomposition, we obtain the two equations for this FR. In fact, FR is just the one scalar equation, but by this artificial decomposition, we obtain the two coupled equations. Okay, they coupled in this way. The growth, this V square growth, for the certain component now put into the first equation, because there is low nu 1/2. Then for this equation there is another nu 1/2. So this is a polynomial. This is a Gaussian. Okay, it decays exponentially. So we can use this exponentially decay to absorb this algebra growth. That's the key point of this decomposition. And the disadvantage of the decomposition is that this guy is the linearized operator. It doesn't like this guy. Okay, it is not self-adjoint. So we have to put the bad guy into the second component. Okay, this is the large velocity component. It means it decays if the velocity is large. Okay, this is bounded term. Okay, this is bounded term. That's the key point to handle the remainder. And also we have to split the boundary condition into two components. One is simple case, it's just the inflow case. One is like the initial boundary condition, but it's different. Okay, in character, because I have said this is the base space. And the condition for the boundary condition for the first second component is more complex. Okay, because we just put the mapping for the one component to the second component. Okay, that means this projection is not standard, and there are error terms. We have to introduce the trace theorem to handle this boundary. Okay. Now we turn to the unsteady problem. We expect the unsteady solution converge to the steady solutions. So we set this perturbation. Okay, this is the steady solution. Just we have talked about previous. Okay, this is the diffuse expansion. G1 is the first correction. G2 is the second correction. This is the remainder. Okay, so this is a typo. Okay, this should be representation 1/2. This is the condition. This is the niche condition. Okay. Then we plug this expansion into the unsteady equation. We obtain the equations for G1 and G2 in this form. G1 is also purely macroscopic. Okay. There's no microscopic, just fluid. Okay. Rho, U, and theta. This is the leading order. The first order, okay, is determined by the unsteady Navier-Stokes Fourier system around the Couette flow. Okay, is a perturbation. And we can go back to this steady problem. Here is the kept phi here. We kept the phi here just to make sure this solution is non-trivial. Because if phi is valid, then we can say that U equals to S theta S equals to US equals to 0, theta S equals to 0 is a trivial solution. Okay, if we want to determine the first correction for the unsteady problem, we must solve this unsteady Navier-Stokes Fourier system. Okay, by usually because the boundary is complex, as I have mentioned in the page 1. It is a mixture boundary condition. Okay, two directions are periodic, one direction is bounded. So the energy method are also applied to obtain the desired estimate. Okay. And this is the remainder for the unsteady equations. Okay. It's much like the steady program. And now, before giving the main result, we introduce some useful function space. And there is also one of our new contribution. We introduce this Shuangqian nanospace. Okay. We also call it LK1 for brevity. LK1 means the take Fourier transform with respect to the direction, periodic direction, and take L infinity or L into norm in the V variable or D variable. Okay. And also we say it much like the Shuangqian nanospace because this norm is in the interior and this norm is outside. Now I give the first result. It is related to the static problem. This is the external force. This is the shear force. If these two forces, both of these terms are small, then we can construct the storm solution in this form. And the F1 is purely macroscopic. Okay, F2 is determined by F1, and this 5 quantities satisfies static Navier-Stokes system around the Couette flow, and moreover, we obtain the estimate for the remainder. In this sense, okay. In this sense, we just prove the hydrodynamic limit, okay. And the second result is related to the static problem. This is the initial data for the kinetic part. This is the initial data for the fluid part. And both of them are small. Then we can prove the initial data is non-negative, and we can prove the solution is non-negative, and also we justify the hydrodynamic limit in the sense that we can control the remainder in this way. It's complex, but just two norms. Okay, one is L infinity norm, the other is L2 norm. Just keep in mind and skip the detail. Okay, in L infinity norm, L2 norm, and plus the LK1 norm. Now I review some related works just from 3 aspects. One part is related to the Couette flow problem at kinetic level. Generally speaking, there are 2 leading groups. One is Mathematics, and the other is Zifei. Okay, they studied the Couette flow or shear flow problem of the Navier-Stokes equations. They investigate the Landau damping and the threshold of the stability, and also the enhanced K. But this is beyond our today's talk. Okay, and the second part is related to the Couette flow for the kinetic models. Okay, and most of works are focused on the homogeneous Boltzmann equation, and the solutions are constructed in the framework of self-similar. Okay, and recently we construct the global stability for the inhomogeneous problem. Okay, and the second part is related to the connection between the fluid equations and the kinetic equations where Couette flow. Okay, that's more related to our today's talk. Okay, the first result can date back to 1989. Okay, this mathematician called French mathematician. He formally derived the famous Navier-Stokes boundary condition, okay, from the Boltzmann equation. And in 1990s, a specific group studied the hydrodynamic limit of the stationary Boltzmann equation. Okay, this paper considered the isothermal boundary. Okay, today's talk is about the relative motion. Okay, this velocity does not equal to this velocity, so it introduces non-trivial solution. And also, if the velocity is the same, then they can consider the temperature. This T1, this T2. T1 does not equal to T2. This case also introduces another a non-trivial solution. That's two ways. There are 2 ways to consider the non-trivial solution. One is the relative motion. The other is the isothermal, non-isothermal. Okay, this is related to the isothermal T1 equals T2. This is related to the T1 does not equal to T2. Okay, and 1D case. And later, Gauss group considered the general 3D case. Okay, and they allow the temperature different, but but only in this order. Okay. The variation of the temperatures depend on this Webster power. Okay. And this paper we justified this former derivation. And recently, Guo's group also considered the case. This does not depend on epsilon, just O1. Okay, they considered 3D stationary programming. Okay. Now we just skip the difficult ideas used in the paper. Okay. Because we consider the boundary value problems, the main difficulties in the study of the boundary value problem for the kinetic equations stems from this convection term. Okay. By the classical PDE method, just we use the tangential derivative to estimate the normal derivative. We can see that the normal derivative blow up. Okay, so that means even for this transport equation, the H1 norm will blow up. Okay. So if we consider the nonlinear problem, we cannot work in soft-left space because the boundary lack of regularity. And in 2010, Guo developed the infinity L2 method to overcome this difficulty. By this new approach, they use the L2 norm to control the L infinity norm. And because L2 norm is easily to be obtained just by energy method. Okay. By this approach, the key point is to convert the L1 norm into L2 norm. Okay. If we use this transformation, then we should consider this Jacobian. Okay. This Jacobian will cause this singularity. Okay. In 3D case, this singularity is -3. Okay. Just if we go back to this L2 norm, then we got the singularity -3/2. Okay. Later, they invented another approach. They improved the L2 norm into L6 norm. So the advantage of this new L2 estimate is here. The singularity is still -3, but L2 norm is divided by 2. For L6 norm is divided by 6, so the singularity decrease one order. Okay. However, they just eliminate the one order singularity for the macroscopic part. This P projection means macroscopic part. For the microscopic part, there is still a singularity here. -3/1. Okay. So to handle this guy, they have to use the T derivatives, and also L6 norm is not enough to close the energy estimate. They have to use the L3 dissipation. L3 dissipation. Then how to obtain the L3 dissipation? They have to use the velocity average lemma. To use velocity average lemma, they have to consider the Couette problem. Okay. Then they use the extension method. Is very complex. Okay. To use this method. In 2021, we developed another approach called the Wiener algebra, and they use this new norm LK1 is a algebra. Okay, by this norm we can convert the 3D problem into 1D problem because we take Fourier transform. Then the derivative becomes multiplier. Okay, so we use consider this Jacobi. The singularity just -1. Okay. So by this approach, we can control the remainder. But for this new asymptotic space, we have to develop some new estimates for these nonlinear operators. This nonlinear operator is different from our previous work in 2021 because this Q is not perturbed. In this paper, we consider the nonlinear. We also got some estimates for the nonlinear operators, but they are perturbed. But this guy is not perturbed, so we have to pay extra effort to control those nonlinear terms in these new norms. Okay, and also this is the dissipation, much like the dissipation norms. Okay, because related to the T integration, time integration. Now we go to the details of the proof. Okay, this is the static problem. Okay, we do this expansion and we obtain the coefficients F1, F2 first. Okay, so to determine this US set S, we need to solve this beneath the problem, and it's not standard because the boundary is complex. Okay, and also we consider this norm, this LK1 Liu norm. We cannot directly from this equation got that LK1 norm. Our method is lies on the energy method. So we first got the Sobolev estimates in higher regularity space, then use this embedding quantity to get this new estimate. And this is different from the kinetic part. Okay, this is just fluid part, so we can get the higher regularity estimate. And then we go to the remainder, the equation for the remainder. This is the entire solution FR. To handle this, to solve this remainder equation, we use the capital decomposition. Okay, and the proof is divided into 4 stems. The first stem is to control the macroscopic part. Use the dual argument because we cannot use the standard Sobolev space for these kinetic equations. And here we use the conservation of mass to obtain the estimate for the A component. The key point here is that we use the microscopic part to control the macroscopic part. And this is the detail for this microscopic part estimates. Okay. We design a test function and solve this non-asymptotic elliptic problem. And the third step is devoted to the L infinity LK1 estimate. That's capital decomposition. We split the entire solution into 2 parts, FR1, FR2. Then we directly obtain the L infinity estimate by characteristic method. Because this is just the left-hand side just transport. Left-hand subsample. Okay, this is the multiplier operator, and this is the standard linearized Boltzmann operator. This infinity LK1 estimate is not difficult to obtain. Okay. The second stamp is devoted to the L2 LK1 estimate for the first certain component. And this is also standard because the linearized operator here is standard. Okay, it has causticity estimates, so we can obtain the L2 estimate, L2 CV LK1 estimate for the certain component without any difficulty. Okay. The key point here is that this guy is the new difficulty for this step is that this guy is gross. Okay, in the sense that there is a singularity. So to handle this term, we have to introduce the LZY2 LK1 estimate for the first component. And this new L2 estimate is related to the nonlinear estimate in this new function space. Okay. Now we turn to the unsteady problem. First, we do this perturbation and solve the coefficients G1, G2 in this way. Okay. G1 is determined by this unsteady level Fourier system. Okay. We obtain this estimate for the fluid components U and theta. They determined by the initial data because this is a steady problem. And then we turn to the remainder. Just like the static problem, we still use the capacity composition. Okay. And here, the growth, okay, still absorbed by this new 1/2. And we must do this carefully because for the static problem, static problem, we do not use this decomposition. But for the unsteady problem, the estimate for the first component is not so good. So we have to further split the second component into two parts. This is the macroscopic part. This is the microscopic part. Microscopic part put in the first component. Macroscopic part put in the second component. Okay. This is different from the static problem. Now we also prove this stability by 4 steps. Step 1 is devoted to the macroscopic estimate on the steady solution, unsteady solution HR. Okay. This is the key point for the estimate. There is an interaction energy. It's different from the static case. Okay. There is an interaction energy. Okay. The macroscopic part still controlled by the microscopic part. The interaction energy can be controlled in this way. And there is a small parameter, epsilon, so this guy cannot make trouble. And the second step is also use the characteristic method to obtain the infinity LK1 estimate in this form. And this is also different from the steady problem. And because we obtain the infinity estimate for the second component only in a small interval. Okay, only small in time interval. Because the time variable here the this t derivative, there is a epsilon factor in front of t derivatives. That means we obtain the L infinity estimate for the first circular component at the first step should be in a small time interval. Okay. Then we use the bootstrap argument to obtain the corresponding L infinity estimate in arbitrary time interval by this iteration method. Okay. And we also use this exponential decay to control the growth caused by the iteration. So this exponential decay plays an important role to control the growth. Just different from the step case. The third step is devoted to the L2, LK1 estimate for the second component. Okay. This is the standard. The extra work should be how to control the boundary, because boundary is complex due to the artificial splitting. We just make the boundary condition for the first component is easier, okay, and the second one should be complex. So we have to use the trace inequality to control the boundary. The boundary for the second component, and the final step is devoted to the L2 estimate, L2 LK1 estimate for the first component. We use this estimate to control the growth caused by the energy method for the second component. This epsilon s square singularity, okay, will be dominated by those L2 LK1 estimate for the first component. This is the dissipation. Okay. That means we have to combine the corresponding L infinity L2 estimate for the two components, and finally we close the estimate. Okay. And all those estimates will be controlled by the initiator, and this is third force and the fluid initiator. Okay. I stop here. Thank you for.
Are there any questions?
That means the particle act to the boundary, then they reflect random. That's the diffuse reflection. They obey this probability. This probability law. Okay. This is the Maxwellian distribution.
Negative.
Oh yeah.
Who are?
Yeah, because two boundary. This for this upbound.
Oh.
This go out. Yeah. This, yeah. Yes, because this is for this boundary is outgoing, and then this is incoming. Incoming part is determined by the So this is the normal derivative. Okay, this is the incoming part. Incoming part is determined by the outgoing part. This is incoming. This is outgoing. So this thing equals 1. This thing minus 1. Okay. This is the incoming. This. Okay. We define this direction the incoming. Okay. This outgoing. They reflect in this way. Okay. Then the incoming part, Vg. This Vg. Matters. Okay. This outgoing, this Vg positive. Okay. The incoming part is determined by the outgoing part. They play this reflection law. And for the Boltzmann is opposite. Okay. This common. This is outgoing. This is
Also, you limit, you can get the limit equation here.
You mean
for this
boundary?
Epsilon go to there.
We obtain the Navier-Stokes or Navier-Stokes Fourier system around the Couette law. This is the steady case. This is the steady case. This is the Navier-Stokes Fourier because they're temperature. Yeah. And these two guys are linked because they we do the perturbation around this Couette law. Yeah, that's sort of Fourier. Yeah.
There's some other condition here. Simply.
Any other questions or comments?
Thank you.